8.1 Objective 2. This section we're going to talk about exponential decay. So let's look. In the NCAA holds the annual March Madness basketball tournament. The top 64 teams in Division I are invited to play each spring. When a team loses, it's out. So let's look. When we've played no games, 64 teams are in. Okay, and again, after we play the buy-ins and all that. After the first round, half of those teams are gone, so there's 32 left. Okay, after the second round, we get to 16 teams left, known as the Sweet 16. After the third round, we get to 8, or the Elite 8. In the fourth round, oddly enough, we get to the Final 4. After the fifth round, we have 2 teams. And after the sixth round, we have our national champion. So let's look at the questions. All right. Copy, complete, and extend the table until only one team is left. We did that. Graph the points on your graph paper. We'll do that in just a second. How many rounds are played in this tournament? 6. Does the graph represent a linear function? No. It's an exponential function. How does the number of teams left in each round compare to the number of teams in the previous round? It drops by half. So let's graph this like it asked us to. Okay, we don't need a super accurate chart here. We'll make the bottoms be the number of rounds. And we'll let the top, and those will be in units of 1, and we'll let the top be number of teams left, and we'll make each one of these 4. 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, 56, 58, or 56. All right, so 64. So when we start, we have 64. After one round, we're down to 32. So 4, 8, 12, 16, 20, 24, 28, 32. Okay, after 2 rounds, we're at 16. 4, 8, 12, 16. After 3 rounds, we're down to 8. 2, 4, 8. After 4 rounds, we're down to 4. After 5 rounds, we're down to 2. And after 6 rounds, we're down to 1. Okay, so in this example, this is how it looks. Okay? That is called exponential decay. An exponential function can be used to model decay when our b is greater than 0 but less than 1. Okay, what was our b that time? Well, after every round, we drop by half. So our b value is 1/2. Okay? So our exponential decay is still y equals ab to the x power. Our b value is just less than 1. All right. Without graphing, determine whether the function y equals 14 times 0.95x equals exponential growth or decay. Well, my b value is less than 1, so it must be decay. B is less than 1, so it must be decay. Okay, without graphing, determine what represents growth or decay. Well, that's 0.12, so that's decay. That's 5, so that's growth. And that's 1/2. Well, that's less, so that's decay. So the first one was decay, the second one was growth, and the third one was decay. Pretty simple, right? Okay, observe my b value. It tells me if the graph's going to go up and to the right or if it's going to go down and to the right. An asymptote is a line on the graph that approaches x or y and increases in absolute value. Okay, so the asymptote is a line that a graph approaches as x or y increase in absolute values. So graphing exponential decay. So here we go. Y equals 24 times 1/2 to the x power. Identify the horizontal asymptote. Okay. So when x equals -3, y equals 192, so on and so forth, and you just plug in points and you keep going. So you graph the coordinates. So as x increases, y approaches 0. Does that make sense? As x increases, we go to the right, y approaches 0. It will never get to 0, though. It will never, ever get to 0. So the asymptote is the x-axis, or y equals 0. All right. Graph y equals 24 to the 1/3 power, or times 1/3 to the x power. Identify the horizontal asymptotes. Okay. Okay, so for the first one, let's make x and y values. So, if x equals -3, y would equal 24 times 1 to the -3. Okay. So let's look at that for a second. How do I get rid of the negative sign? So that's going to be 24 times 3 cubed, which would be 24 times 27. So that's going to be a really, really big number. So let's try when x equals -1. Y is going to be 24 times 1/3 to the -1 power. Okay. So that's just going to be 24 times 3. It's still a pretty big number. So when x equals 0, y is going to equal 24 times 1/3 to the 0 power, which would be 1, which would be 24. So when x equals 1, it'd be 24 times 1/3, which would be 8. And when x equals 2, it'd be 24 times the 1/3 or 1/9 power, which would be 24/9. Okay, and you could go on and on and on and on, and what you're going to find out is it's never going to approach 0. So let's plot the points and check it out. So when x equals -3, -1, 2, 3, y equals something really, really high, way up there. When x equals -1, it's going to equal 70, so it's way up there too. So when y equals 0, or x equals 0, y equals 24. So let's make each of these 4. 4, 8, 12, 16, 20, 24. Okay, so when x equals 1, y equaled 8. When x equals 2, y equals 24/9, which would be 2 and some change. And we could go ahead, let's do when x equals 3. Okay, that's going to be 24 times 1/27. So that's going to be a little bit less than 1. And so on and so forth. So we're going to look at something like this. It's going to go on forever to the left, and it's going to curve. And my asymptote is 0. Okay, graph y equals 100 times 0.1 to the x power. And again, you're going to find out it's going to look the exact same way, and it's going to have an asymptote of 0. Okay, moving on. Real world connection. Depreciation. The exponential decay graph shows the expected depression for a car over 4 years. Estimate the value of the car after 6 years. So the decay value is B, which is equal to 1 plus R, where R is the annual rate of decrease. The initial value of the car is $20,000. After 1 year, the value is $17,000. So write our equation for R. R is the final value minus the initial value over the initial value. So that's 17,000 minus 20,000 over 20,000, which equals -0.15. So our B value is going to be 0.85. And you can see to the work to the left why that's true. So write a function and then evaluate it for x equals 6. So y equals ABX. Let's look at our graph. We know when x equals 0, y equals 20,000. So I got 20,000 equals A times 0.85 to 0 power. So we know 20,000 equals A. So we can say y equals 20,000 times 0.85 to the x power, which they want us to solve for 6. So now just plug that in your calculator, and you're going to get y equals $7,542.99. All right, so after 6 years, that $20,000 car is only going to be worth $7,500. Okay, let's look at the last example. So estimate the value of a car after 10 years. So our equation last time was y equals 20,000 times 0.85 to the x after 10 years. So y equals 20,000 times 0.85 to the 10th power. This looks like a great job for our calculator. Okay, let's just get it set up. So we need to go 20,000 times 0.85 raised to the 10th power. So what we're saying is the initial price was $20,000. We have an 85% or a 15% depreciation value, and we're doing it for 10 years. So it's going to be around $3,937. So around $3,937. So about $3,900. Okay. All right, that concludes this lesson for 8.2b.